Good evening, everybody. I'm Steve Barrett, and this is the ABC of Stars and Galaxies. It's a short talk, no more than 2 or 3 hours, tops, and then you can get back to the lovely Gaia behind me. So I'm talking about stars and galaxies. When we look out into the universe, we see beautiful structures that are out there. Difficult to see with the naked eye, but with telescopes these days, we can get superb images of lots of different galaxies, lots of different shapes, lots of different sizes, lots of different distances. And thanks to especially space telescopes, we get exquisite detail in a lot of these galaxies. And galaxies, of course, are big star cities. They are made up of billions, perhaps even trillions of stars. And we can ask ourselves, how did they come to be? How do you make a galaxy? How do you make a star? So that's essentially what I'm talking about. It's only going to be half an hour or so. So of course I can't go into a huge amount of detail, but I've tried to distill how we think about galaxies forming to the ABC. A for accretion. Accretion simply means growing by gravity, pulling together lots of gas in the very early universe, and all of that gas accumulating so as to form galaxies. We'll see a little simulation of that in a moment. The B of the ABC is for black holes, because as far as we can tell, at the center of every galaxy, there seems to be a large black hole, a so-called supermassive black hole. And these might be sucking in a lot of material around them, and they might be a little bit like the black hole at the center of our galaxy, not doing much. They don't appear to be feeding on neighboring stars. There isn't a lot of matter falling into them. And the C of the ABC is the third factor that allows us to understand how galaxies behave, and that is collisions. Because galaxies, although we think, well, we on Earth, Gaia, moving around the sun is part of our galaxy, we don't think of the fact that galaxies actually crash into each other now and again. Not very often, but on the timescale of the universe, galaxies are always colliding with each other, and that's how galaxies grow. What about stars themselves? Well, we haven't got time to make this a physics talk or a talk about stellar evolution as such, but we can, if you like, give you the instructions, the recipe for how you can make a star for yourself. If you start with a very big cloud of hydrogen, the lightest element in the periodic table, so the lightest gas, lots of hydrogen was made in the Big Bang. The Big Bang, 14 or so billion years ago, made an awful lot of hydrogen. It only took about 3 minutes to make all of the hydrogen in the universe. If you start with a big cloud of hydrogen, step A is wait a while. Step B is wait a little longer. And step C is wait a little longer still. And then you're done. Now you have a star. In other words, that's all you need to do, is collect together some hydrogen. As long as you've got enough of it, gravity will do its stuff, and that cloud of hydrogen will collapse until you have a star. So in that sense, making stars is easy. Perhaps that's no surprise, because the universe has made trillions upon trillions of stars over the last few billion years, so I guess it has to be easy. How do we know how things behave? Well, most of what we understand is based on observing stars and galaxies, and more recently, doing computer simulations. You don't have to worry about all the detail on the left-hand side. I'm simply trying to indicate that there are dozens, possibly hundreds of different computer programs that are all trying to simulate how does the universe work, how do stars collapse, why do they shine, why do they have different colors, why do they have different temperatures, why do galaxies look the way they do. A lot of our understanding has come in the last 10, 20, 30 years because computers are powerful enough to simulate realistically how these things behave. And based on our understanding, partly from simulations and partly from just thinking about it really hard, because when we observe the universe, it appears to be expanding. In other words, the distance between galaxies appears to be getting larger and larger and larger as time goes by. If the universe appears to be expanding, then we can say, well, in that case, it used to be smaller. If we wind the clock back, if we wind it back 14 billion years or so, then instead of having a universe which is vast, hundreds of billions of light years in diameter, you can say that if you go back in time far enough, everything that we currently see, all the galaxies, all the stars, everything that we can observe, used to be in a volume only a few centimeters or so across. It's impossible to imagine everything in the universe compressed into such a small volume, but to the best of our knowledge, that's what happened in the Big Bang 14 or so billion years ago. The universe, just like a golf ball, had dimples in it, not physical dimples, but variations in density and variations in pressure. And if we look at a very small section and ask a computer, if we take a small volume of the universe and ask what would happen if we let gravity loose on that, then the simulation tells us that what happens is the universe ends up looking like this simulation on the right-hand side. Gravity makes dense parts even denser and light parts even lighter, and the white here indicates very dense regions of the universe. We end up with this web-like structure, and on the largest scale, that's what we think the universe actually looks like. Where these various filaments of this web intersect with each other, we get these white blobs. Those white blobs are the galaxies and clusters of galaxies. In other words, when we let gravity do its stuff, we just start with a very large amount of hydrogen, let gravity do its stuff, we think we end up with this structure, and that structure looks very like the structure we see when we turn the world's largest telescopes into the very, very distant universe. Simulations are not easy to do. It's not simply a question of, well, we just have to throw in a large amount of hydrogen. Gravity is simple. Things attract each other. That's all it is. But unfortunately, the simulations do have to take into account a lot of very complicated physics. It's not simply a question of saying, well, gravity pulls everything together. Generally speaking, it does try to. But also we have to worry about the fact that when gravity pulls things together, it makes stars. And stars live and stars die. And when stars die, they might go supernova and produce an explosion which tends to push material out. Gravity is trying to pull everything in, but supernova are pushing things out. And it's a balance, it's a tug of war between these various things that decide how stars form and how galaxies form. We also have to worry about not only how gravity pulls and supernova and black holes might produce radiation that push out, we have to worry about that the universe is full of stuff that we don't really understand. The sort of matter that we are made of, and as far as we can tell, so is the rest of the solar system and the rest of the Milky Way galaxy, and as far as we can tell, every other galaxy that we can see, all of those trillions of galaxies that are out there, they all seem to be made of the same stuff. And yet, there's an awful lot we can't see that we're calling rather enigmatically dark matter. We think it's out there because of the effect it has, the gravitational pull that we can detect on other objects, but we can't actually see it and we don't actually know what it is. But somehow we have to include that in the simulations in order to get a universe that looks like the universe in which we live, in which case we can then believe these computer simulations. So the cosmic web, this web structure on the largest scales, we can't see stars on this scale, we can't even see galaxies. The best we can hope for is to say one of these little white blobs is probably a small collection of galaxies. And we think what happens is gravity pulls the various atoms of hydrogen that have existed since the very early universe, and they filter down these filaments and start collecting or accreting into these blobs. So if we just look at one of those and ask, let's look in more detail at how a galaxy actually forms. So here we're looking only at one galaxy. So we think matter is coming down from above and coming in from the bottom right and coming in from the left. And if we run the simulation over 1 billion years or so, we can start to see matter falling into this central region, and you can see that it's falling in such a way that it's starting to spin up the galaxy. Bright here means dense and hot, and a darker color, this dark blue or black in the background, is very low density. So you can perhaps see that gas is being used up. We're getting darker and darker in the corners and getting brighter and brighter in the middle. Matter is flowing in and producing this sort of whirlpool. It looks a little bit like you would expect water flowing out of a bathtub. It's not so different to that. Matter is falling in, and we are producing something which already looks a little bit like the galaxies we saw in the very first slide of the talk. So we have some understanding of how we can start with a very large amount of hydrogen and end up with something that looks a little bit like a galaxy. That's a real galaxy. That is a picture from the Hubble Space Telescope of a galaxy called the Whirlpool Galaxy. We still have some work to do to understand all of the structure within that galaxy, but we can get an idea of why galaxies form and why they end up with this rather beautiful spiral arm structure by doing these simulations and seeing what we get. So this galaxy might have many hundreds of billions of stars, maybe as many as 1 trillion stars. As well as the white, which indicates a lot of stars are shining, you also notice lots of blobs of pink all over, especially in the spiral arms of the galaxy. These pink regions are clouds of hydrogen that haven't yet formed stars. And if we have a look more closely at some of them, anybody that's an amateur astronomer might recognize this. This is the Great Nebula in Orion. So this is visible with the naked eye, and even through a pair of binoculars or a small telescope, it is a quite spectacular sight. Generally nowhere near as colorful as this image would indicate, because this is an image taken with a large telescope, and then the colors have been enhanced to show us what's actually there. But this is a stellar nursery. This is a large cloud of hydrogen which is slowly collapsing, and stars are being born right in the center of this cloud, which we call a nebula in the astronomical sense. We can again run a simulation to ask, can we understand how it is that a large cloud of hydrogen collapses to form stars? This might at first sight look like a close-up of a star, but no, this is a large cloud of hydrogen. It's a large sphere. That's not very realistic, because most clouds of hydrogen that exist in our galaxy are very ragged, much like clouds you see in our sky. But for the computer simulation, it's easier to start with a large circular body of hydrogen. Each little bit of hydrogen is given a small nudge in one direction or another, otherwise it would simply collapse to a point and produce a black hole. So in this case, every little bit of this large cloud is given a small nudge in one direction or another at random, and then again we let gravity do its stuff and then monitor over the next few million years what actually happens. And this simulation shows that some bits of the cloud actually go out. They happen to be going in that direction, but gravity is pulling most of the material in towards the center. And again, the yellow parts, the brighter parts, indicate we are getting more dense regions and hotter regions of this hydrogen cloud. So you can see it's getting more and more yellow in the middle there, and stars are eventually born. Once the pressure and temperature are high enough, we can fuse elements, which releases energy. It's nuclear fusion, releasing energy, and stars begin to shine. You can see after a while it starts to look like a popcorn machine. There are so many stars being born from this huge cloud of hydrogen, which might have started life as maybe tens of light years in diameter. It's producing huge numbers of stars, not just a few dozen, not just a few hundred, but it looks like a large cloud of hydrogen generates thousands of stars. And we can ask ourselves, well, is that realistic? If we back off a little bit, we can see that our large cloud of hydrogen now looks rather ragged. There's still some hydrogen there, there's still some red there, even though we've generated, or even though we've made thousands of stars in this star cluster, we still have some hydrogen left over. And that's fairly typical. You don't necessarily use all of the ingredients when you're making stars. But we can ask ourselves, well, if we think that's what the computer simulations are telling us, start with a large amount of hydrogen, let gravity do its stuff, we would end up with a sort of cluster, a peppering of many thousands of stars. Is that what we actually see? When we look out into the Milky Way galaxy, do we see lots of star clusters that look like that? And the answer is yes, we do. We see lots of star clusters that look like that with many, many thousands of stars. We think our sun was born that way, but we don't appear to be in a star cluster anymore. So maybe lots of stars were born, but maybe our sun got thrown out of this cluster, and we don't know which cluster that was. We can no longer recognize which cluster in the Milky Way might have been our sun's birthplace. Our sun was probably thrown out and is now effectively a star all on its own. But it is quite common when we look into the Milky Way galaxy to see lots of clusters where stars have many thousands of immediate neighbors. The way stars work, again, we're not going to go into the nuclear fusion and all the details, but all stars are determined by balance. Gravity is always trying to make the star smaller, regardless of how big it actually is. Gravity always pulls inwards. And if a star is hot enough at its core, then nuclear fusion will occur. That's the fusion of the nuclei of atoms. The center of atoms are fused together, which releases energy, and the fusion core of a star will produce radiation, which effectively pushes outwards. And all stars are a balance between those sets of opposing forces. Gravity is trying to make the star smaller. Nuclear reactions at the core are trying to make the star bigger. And as long as those two are in balance, then the star is happy. That's the situation for our sun. Gravity is trying to make it smaller. Fusion at the core is trying to make it bigger. And for billions of years, those forces have been opposing each other, and the sun has been stable. If at any time they get out of balance, in other words, what happens when the star runs out of fuel? What happens when it can no longer produce nuclear reactions at the core? Then gravity will win over the radiation pushing out. That's not going to happen for our sun for many billions of years. Don't panic just yet. We've got enough fuel for the sun to last for another 5 billion years or so. So don't panic. But that is why stars evolve. When fuel runs out, those forces are no longer in balance. The balance is destroyed, if you like, and that means then the star has to evolve. It must change when things get out of balance. And we can understand why stars are the way they are, why they have a particular lifetime, based on understanding the forces and the balance between those forces inside a star. Of course, we can't actually look inside a star. We have to rely on our understanding of the laws of physics to tell us that must be what is happening inside stars. And it helps when we're thinking about stars to look at where they are, especially if we want to understand the evolution, how stars change. It helps to plot them on a diagram here, where the vertical scale is how bright they are, brightest at the top and dimmest at the bottom, and the horizontal scale is how hot they are, done in a rather odd way, in which it's hottest on the left and coldest on the right. And also there's a color scale there, because the cooler stars are mainly red and the really hot stars are mainly blue. So you can either think of it just as the color of the star, or you can think of it as how hot the star is. There's our sun, sort of in the middle of this diagram, because our sun is a relatively average star. It has a luminosity, it has a brightness, which we call 1, simply because we say, well, let's think about brightness in terms of how bright the sun is. So by definition, the sun has a brightness of 1, and the surface temperature of the sun is a little shy of 6,000 Kelvin, 6,000 degrees C, roughly speaking. Sounds pretty hot, but that's rather modest for a star. When we think about what's going to happen to a star, we can refer back to that diagram of where the stars are in terms of how bright and what color. So this is how we think stars change during their lifetime. A star would probably start as a large cloud of hydrogen, which starts to collapse under the influence of gravity. Remember, this is one of those little pink regions that we saw in the large Whirlpool galaxy just a little while ago. A collapse of a cloud could produce a star like our sun, for instance, what would be classified as a relatively small star. In other words, our sun is not particularly large. You might even call it a dwarf star. So if the collapse of a hydrogen cloud produces a small star, that star will probably live for many billions of years, just like our sun. It eventually comes to the end of its life because the fuel starts to get used up, the forces become out of balance. What will happen is the outer part of the star will get shrugged off into what's called a planetary nebula. Nothing to do with planets going around the star. A planetary nebula is simply the name given to what happens when the outer part of the star gets shrugged off and ends up flying out into the space between the stars. They're called planetary nebula simply because a long time ago, when they were first seen, they were confused with planets because they look a little bit like disks, especially if you're looking through a relatively poor quality telescope. What happens when the outer part of the star is shrugged off? Well, the inner part of the star, the core, is left behind, and that's called a white dwarf. This is what ultimately is going to happen to our sun. In 5 billion years or so, our sun is going to look very different, with a large nebula, a huge great nebula, light years across, and a tiny white dwarf star, barely any bigger than the Earth, left as the core. If we see where they are on the diagram, when the sun starts to run out of its fuel, it's going to get larger and larger and redder. Because it's very large, it ends up above, in this diagram, above where the sun is. It's more luminous, it's brighter, simply because it's bigger. But it's going to be redder, so it's going to be further to the right on this diagram. So these so-called red giants are up here to the top right of where the sun is now. The core that's left after the sun loses its outer atmosphere is called a white dwarf. They are relatively small, so they're not very luminous, so they're further down on this diagram, but they are relatively bright in the sense of they are bluish, whitish stars, and hence they're over here with a much higher surface temperature compared to a red giant. So by looking out into the universe and seeing what colored stars do we have in terms of what is their brightness and what is their surface temperature, we can get an idea of how far along these stars are in their evolution. If they're like the sun and they're down here, we know that they are the cores of old stars. Red giants are stars that are coming to the end of their life by using up all of their fuel. It is possible that when a large cloud of hydrogen collapses, it makes a star that's bigger than our sun. It might be 10 times the mass of our sun it is possible to produce. Large stars use their fuel very quickly. They don't last like our sun for billions of years. They might only last for millions of years. That might sound like a very long time, but remember, it's thousands of times shorter than the lifetime of our sun. Again, when the fuel runs out, which will happen quite quickly for a large star, the star will swell up, and it won't necessarily simply quietly shrug off the outer layers of the star's atmosphere. It could, if it's massive enough, end its life as a supernova, which goes bang with a capital B. It could blast out most of the material inside the star into the space between stars, the so-called interstellar medium. What's left behind? Well, through a mechanism that we are still studying and scientists are still trying to get their heads around, when most of the material gets thrown out in a supernova explosion, what's left in the middle gets crushed to very, very high density. In other words, remember, the white dwarf here was about the size of the Earth, but the star that's left behind after a supernova might be a neutron star, which is only a few kilometers or tens of kilometers in size. It's not the size of the Earth, it's not the size of Gaia, it's more like the size of a city. A similar mass to the mass of a white dwarf, a similar mass to the mass of our sun, but in a sphere that's only kilometers in size. Very, very high density. And if it's in the extreme case, in the highest densities, it might form a black hole. A black hole is a region of space in which matter has been compressed to such very high levels, then the speed at which material would have to be thrown off to escape from that particular star is so high, not even light can escape from this star, and hence we label these things black holes. But notice that in both cases, the star either shrugs off some of its outer layers, or most of the material is sent out into space and only a tiny bit left behind. In other words, a lot of material is simply recycled back into the space between stars, where that material can go on and build a second generation of stars, which eventually will go through the same cycle, shrug off a lot of the material or end its life in a supernova, and the material will go cycling round again and again, or this way again and again. Stars are the ultimate recyclers. For billions upon billions of years, stars have been recycling material. And given that in the centers of stars, I said nuclear fusion was occurring, fusion means taking light elements and fusing them together to make heavier elements. And I'm sure you're all familiar from either your school at the moment or your school days from maybe a few decades ago. You remember the periodic table of the elements telling you that hydrogen is the lightest element, and we've got lots of heavy elements down at the bottom of the periodic table. Well, stars are basically responsible for the periodic table in the sense that the universe made shed loads of hydrogen, and ever since the Big Bang, stars have been fusing hydrogen into heavier stuff like helium, and then fusing helium into carbon and nitrogen and oxygen and calcium and phosphorus and all the things that we need to live, all the way up to iron. I'm not going to talk about why iron is so special, but we have to ask ourselves, well, okay, what about the really heavy elements like silver and gold, etc.? Are stars responsible for making those in the same way, by fusing atoms together, fusing nuclei of atoms together to make heavier and heavier nuclei? As far as we understand it, the heavy elements come when a star shrugs off its outer layers. That's what our sun ultimately will look like in a few billion years' time. But if a star goes supernova, then it will effectively redistribute all of the elements it's made up to that point. If it's made hydrogen into helium and carbon and oxygen and silicon and all these other elements, when a star eventually comes to the end of its life, if it's massive enough, all of these elements will be redistributed back into the galaxy, and they will be the ingredients for the next generation of stars. That's why when we look into the Earth, we find not just carbon and nitrogen and oxygen, we find loads of heavy metals as well, like copper and silver and gold. They came from stars exploding an awful long time ago, because our sun didn't simply come into being from the hydrogen made in the Big Bang. Our sun came into being because it was the last of a long number of generations. Many generations of stars existed, created heavy elements, redistributed them, recycled them, another generation, another generation, another generation. Eventually, along came the sun and took some of those light elements like carbon, nitrogen, oxygen to make us, and used some of the heavy elements that are now dispersed in the Earth's crust that we can see if we do a little bit of digging. How do we know what's at the heart of our galaxy, or indeed any galaxy? It's a little difficult to view the center of our galaxy simply because it's so crowded, which is why until a few years ago we really didn't know quite what was at the center of our galaxy. It's very dusty and there's a huge number of stars in the way. But recently we have got a much better idea of what's going on. And if we take a look at the stars at the center of our galaxy, we find that if we map out how those stars are moving, the stars appear to be orbiting something which we cannot see. We can see stars close to the center of the galaxy, but the stars are in orbit around something that must be very massive to keep these stars in orbit, and yet we can't see what it actually is. If it's very massive but invisible, we think that is a candidate for a black hole. So this experiment has been done for quite a few years. For over a decade, astronomers have been watching stars close to the center of the galaxy, mapping out how they move, and deducing what must be at the center of the galaxy in order to make them move the way they do. And we come to the conclusion that at the center of our galaxy, there is a black hole. Not a black hole with the same mass as our sun, but a black hole with the mass 4 million times bigger. This symbol on the right-hand side of M dot is just M circle dot, that's just shorthand for the mass of our sun. Rather than talk about the mass of a black hole in kilograms or in tons, we simply say, how big is it compared to the mass of our sun? Nothing special about the mass of our sun, just a convenient unit to use. So in the center of our galaxy, there is a huge black hole with a mass 4 million times the mass of our sun. And part of research is trying to figure out how it got there. Did it form first, and then the galaxy formed around it? Or did the galaxy form and then somehow a black hole form at the center of the galaxy? We're trying to understand the chicken and egg problem of how do galaxies form and how do black holes form at the centers of galaxies. We know they're there, we have evidence they're there, we've even looked in other galaxies. Again, a rather tricky experiment to do, a rather tricky observation, but fairly recently observations have been made of what appears to be a lot of material that's spiraling around a black hole. The black hole is somewhere in that shadow in the middle there, but just like if you're trying to get water out of a bathtub, it doesn't all go down the plug hole immediately. When you pull the plug out, the water tends to swirl around before going down the plug hole. It's the same idea. Black holes don't instantly eat everything around them. Material tends to circulate around the black hole before eventually the black hole consumes it. And what we're looking at here is material that's effectively circulating around the black hole, getting very hot in the process and radiating light, radiating energy. And this has been seen in a galaxy quite some distance away, but this particular black hole isn't millions of times bigger than our sun, it is some few billions of times bigger than our sun. So clearly these black holes can end up as absolutely huge. And again, we're trying to figure out how that can be. Now, if you look at an image of a galaxy, you might say nothing interesting is going on there. Remember, we can't really see the black hole at the center, especially in a picture like this, because it's very small and it's so crowded there, we can't see really what's going on. But when we look at images like that, we might get the impression that galaxies look very sedate. They look very static. We sort of know that they are actually rotating, a bit like big Catherine wheels. But when we look at a picture like that, we can't sit and watch galaxies rotate because they rotate too slowly. It might take hundreds of millions of years for a galaxy to rotate once. And none of us have got the patience to watch that. So we end up with pictures like this, again from the Hubble Space Telescope, and we say, well, it looks like nothing interesting is happening. Over a lifetime, however, there can be significant interactions with other galaxies. We can see that in other snapshots. For instance, we take a snapshot and we see what looks like two galaxies interacting with each other. They are close to each other. They seem to be distorting each other. But again, it's only a snapshot. It's one picture of a pair of galaxies, and we're having to make guesses about what we think is actually going on. If we want to understand exactly what the influence of collisions between galaxies are, having snapshots like this is useful, but even more useful is again getting the good old-fashioned computer to say, right, let's do a simulation of what would happen if this galaxy comes crashing into that galaxy. Does it produce the sort of structures that we actually see in the universe? So it's always a combination of observation of what's actually out there and computer simulations telling us, have we got the physics right in terms of can we explain why we see the structures that we do? And we can only really appreciate the dynamics of how galaxies behave by running simulations, in here the early universe, and we see that galaxies are not static, separate entities. Each little blob here is one galaxy. We're not seeing any individual stars. And you can see that it's an absolute galaxy soup here, and galaxies are all over the place. Notice there's two very bright galaxies in the center here. They are tugging on each other, and eventually they are going to merge together as one even larger galaxy. And there's lots and lots of smaller galaxies around as well. So by running simulations like this of what we think the early universe was like, we can get a sense for how galaxies have interacted with each other and how they have grown over billions of years by literally being cannibals. They eat each other, and galaxies can collide with each other, merge with each other, and basically cannibalize so that galaxies grow over billions of years. And it's really only with computer simulations that we gain that level of understanding. So I remind you that galaxies formed in the first place because the universe made a lot of hydrogen in about 3 minutes or so, and over billions of years, gravity took hold and started pulling all of that hydrogen together into denser and denser regions. Black holes exist at the center of, we think, every galaxy, maybe even the center of some star clusters as well. We don't understand the mechanism by which that happened. We don't know if black holes came first and then galaxies formed around them, or whether galaxies formed and then black holes formed. But that's why we have telescopes around the world and telescopes in space looking at the universe to try and answer questions like that. But we do know that collisions have been an essential part of how galaxies have come to end up looking the way they do. So that is the A, B, C of stars and galaxies. Thank you very much.